Good morning, students. So we are going to discuss the new topic, which is on adiabatic and sudden approximations. And we have been discussing so far on time-dependent perturbation theory, and the Hamiltonian depends on time. And this time-dependent perturbation theory, the perturbation effect is very, very small. So we are going to consider the time-dependent Hamiltonian and the related factor lambda are very, very small. And we have not considered the rate of change of Hamiltonian. We have considered only so far the time-dependent Hamiltonian, whereas we have not considered the rate of change of Hamiltonian. Rate of change of Hamiltonian means dh by dt. dh of t divided by dt. Okay, your h of t means perturbing field which depends on time. Okay, h of t means perturbing field which depends on time. And of course, this term is very, very small. But we have not considered the rate of change of perturbing field. How it affects the transition, probability transition. How it affects. And this rate of change of perturbing field can be either slowly or gradually increasing function, or it can be suddenly increasing function. Okay, it can be both ways. So I repeat, the rate of change of Hamiltonian can happen either sudden or fast, okay, or rapid or abrupt. Suppose if it increases gradually, so slowly it increases or it changes, what we call this as adiabatic approximation. Okay, I repeat, your dh by dt, which is nothing but rate of change of perturbing Hamiltonian. Okay, so we know this one. This rate of change of Hamiltonian changes slowly or gradually, and this term is known as adiabatic approximation. Suppose if it changes very fast, the change happens very abruptly or rapidly, then this is known as sudden approximation. Okay, so one is adiabatic approximation, another one is sudden approximation. How dh by dt changes. Okay, so we know this expression very well. So right from the first order correction of time dependent perturbation theory, we learned this term, which is nothing but your amplitude. The square of the amplitude will give us transition probability. We know already this. Okay, the transition probability mainly depends on both factors. One is harmonic term, another one is perturbing field, time dependent perturbing field. So now there are only two terms. Okay, how to remember easily? We'll see small technique. Now you are going to keep this term constant and you are going to differentiate. You are going to change. Second one, we are going to keep this term constant. We are going to differentiate this. Okay, so this, suppose if it changes with time. Okay, if it changes with time, that means we are going to keep this term is constant. Suppose we are going to keep this term is changed, we are going to keep this term as constant. And one is for adiabatic approximation, another one is for sudden approximation. We are going to differentiate this. Keeping this as constant is for technique for adiabatic approximation. Keeping this as constant, we are going to change this one is for sudden approximation. So that's all. So we are having two terms. We are going to keep one term as constant. We are going to change one and get the expression for adiabatic. We are going to keep this one constant. We are going to change this one, another expression for sudden approximation. That's all. So that's the idea. In both the cases, we are going to find out the transition probability using first order correction of time dependent perturbation theory. Okay. So the diagram says about how gradually changes and how the wave function changes abruptly. And of course we know the wave function for the infinite quantum L is given by this graph. We know already. So psi versus your L. Okay, psi versus L. And we have both the infinite walls and this is your wave function. In the first case of adiabatic approximation, Suppose I am going to bring this wall, I am going to take this wall to that side, say from L to 8L. So your size of the wall is say 0 to L, and I am going to take this wall to 8L. Okay. In the first case, what I am going to do is, I am going to take the wall slowly. I am going to take the wall, because slowly means adiabatic approximation. I am going to take this wall very slowly or gradually. When I am going to take this wall to 8 side very slowly, the wave function also will follow the same thing. Correct? You have one wall, rigid wall. This is movable wall. Wave function exists in between these two walls. I am going to bring this wall slowly. The wave function also will move along with the wall. You just imagine. So it means that in adiabatic approximation, particle will remain in the ground state always. Because look at, this is in the ground state. Okay, this is also in the ground state. So when you take the wall slowly away from the original position, and adiabatic condition will be satisfied. Suppose we are going to take this wall suddenly, rapidly, very fast. And what will happen? The wave function, look at the wave function, and here up to here it will be ground state. So this is, the particle will left momentarily in its initial state. See? That's the difference between these two. So very important 1 mark question. Okay, this will come. So in time dependent perturbation, we have dealt the case of perturbation which is very, very small, but we have not considered the rate of change of perturbation. We have not considered so far. In this section, we are going to treat the perturbation not only small but also switch on either adiabatically or suddenly. Adiabatic means slowly, gradually. You are going to switch on, switch off. Okay, so sudden as well adiabatically. First is switched on at a time t equal to 0 and off at a later time t. Turning on and off may be smooth or rapidly. So we know this expression, we are going to use this expression. So now we are going to discuss in detail about adiabatic approximation. So here a slowly varying potential is considered. Okay, Hamiltonian of the system evolves slowly with time, your h of t. H of t is switched on at a time t equal to 0 and h of t is switched off later at time t equal to 0. So you are going to switch on now. Okay, after some time you are going to switch it off. Okay, we have not paid the attention to the rate of change of perturbation so far with respect to time. H of t vanishes at t equal to 0 and at a time t equal to t also. It's a very important concept. See here, for example, at t equal to 0, there will be no time. Okay, at t equal to 0, so there will be no wave function. H of t will not be there. Then h of t will exist. At some time t equal to t, I am going to switch it off. At that position also, h of t will vanish. It will become 0. Okay, that's why it's given as h of t vanishes at t equal to 0 as well at t equal to t, because this will not appear. This will not appear. Okay, this can be extended to a more general problem in which the perturbing potential undergoes large changes, and this is a slowly varying potential according to adiabatic perturbation. If it is very, very slow, almost this can be kept as a constant because it's slowly varying potential. So this will be kept as almost constant. Okay, we are going to use this one. So we know that first order transition probability from time dependent perturbation theory is given by this expression. We know already, we have already learned. Okay, that one. Squaring that will give you transition probability. So this is your expression for amplitude, and squaring the amplitude will give you probability transition. Okay, transition probability. So this expression is for transition probability. Okay, and we know the perturbing field is given by this. Okay, this matrix element, and omega ml is given by em minus el divided by h bar. We know already. Now in this term, this is harmonic term. This is perturbing field term. As I said earlier, we are going to keep one as constant. We are going to differentiate for one method. We are going to keep another one constant. We are going to differentiate the previous one for another method. That's a technique. Now what I am going to do is, I am going to write this harmonic term exactly like this. How it is possible? E power I omega mlt, which is equal to multiply and divide by I omega ml divided by I omega. Okay, now I can take this term writing this term as differentiation of e power I omega mlt. Correct? You just differentiate this with respect to t will give you I omega ml multiplied by e power I omega mlt. That I omega ml divided by omega will cancel. We will have e power I omega mlt. So I can write this expression as exactly like this. Is it okay? So this expression can be inserted in the previous equation and we are going to get this expression. We are going to integrate this. Is it okay? We are going to substitute this expression here and we have a complete expression, equation 7.105. Now we are going, let us integrate. So we are going to keep this term as u and this term as dv. We know the formula u dv equals uv minus v du. We know this formula. Now u dv, so uv, what is u? So u will be your this term. Okay, u will be your hml, this term. What is b? Your dv is this one. Okay, your dv is this one. What is b? What is the integration of d by dt? That will cancel. Correct? D by dt and integration that will cancel. You will have v will be e power I omega mlt uv term. Okay, minus, already one minus is there. Correct? One minus is there. That minus is here. You have in this formula one minus is there. So minus 1 divided by h power omega n, and we have v du. What is v? V is e power I omega mlt. What is du? Differentiate this. So that will be your. Any doubt? Now, just now we learned that at the moment we are going to switch on and switch off, the h of mlt will vanish. Correct? Will vanish. We discussed. So at time t equal to 0, there will be no h of t. At time t equal to t, and again there will be no time. We will get the same answer. Same answer. So one answer minus same answer. Answer will become 0. So this term will become, this contribution will be 0. Okay, so uv term will become 0. And we have the remaining term. Okay, so remaining term will be minus plus. You will have, you can pull it out. This 1 by h power omega will pull it out. Remaining term you can have this one. Any doubt? So transition probability is given by this expression. Now, since the perturbing field is very small, your dht is all